Welcome to the Calculus, a collection of micro lectures, video lessons, and sample exercises. Limit theorem number 4. The limit theorem for a sum and difference of different expressions. Let us have here separate functions, and we are going to solve for the limit of the sum or difference of these functions using this limit theorem. Starting from here, hopefully you were able to understand the idea of the substitution and why is it the substitution doesn't work at all. You have the previous video for that. But starting here, since it's acceptable generally for substitution process in getting the limit, we are going to use that. But of course, for these theorems, we're going to illustrate them step by step. And if you were able to identify already a specific step or a shortcut in what you do, as long as it's mathematically correct, we're going to accept that. Let's consider here f of x is equal to a certain function 2x plus 1. Let's have g of x being 4x minus 9. And what if we have h of x which is equal to 6 minus x? Now, this theorem talks about the solution of the limits if these functions are already added or subtracted, but they already have the results. Say, for example, the limit for f of x as x approaches to a certain constant is L. We already have the L, okay? Assuming we already have the value for the L. For g of x as x approaches the same constant C, what if it's M? And for the limit of h of x as x approaches to the same constant, what if we have N? This theorem tells us this very simple idea. If we have here the limit of the sum of f of x, let's just try to use 2 first, g of x, as x approaches to the same constant C, okay, same C, okay? Even without solving for the expression equivalent to f of x plus g of x, this theorem tells us that we simply need to add their limits. L stands for the limit of f of x, and M stands for the limit of g of x. So just like that, no need to solve for this, simply add L and M. But of course, we need to have L and M first. That is if we already have these values. So for illustration, let us try to solve first the individual limits for a certain constant. We have, what if the limit of f of x as x approaches to 1? Okay, this would be equal to, okay, the limit of our function 2x plus 1 as x approaches to 1. So we can use substitution here. 2 times 1 plus 1 will get here 3. That should be our L. Okay, that's our L indicated here. Now, how about for the second function, limit of g of x as x approaches to the same value of 1? So you have here the limit of 4x minus 9 as x approaches to the same constant 1. You'll have 4 times 1 minus 9. You will have here negative 5. Okay, this would mean, going back here, if we are solving for the limit of f of x plus g of x, if x approaches to 1, this is just simply equal to 3 plus negative 5, which will result to negative 2. That's it. If this is because we already have the values here, and the value we're approaching to that is being applied are all equal to 1. Of course, we're going to illustrate it and correct if it's really and verify if it's really correct if we are going to combine first f of x and g of x. Our f of x, this is verification, plus 1. This is a verification to see if the theorem is really correct. Minus 9. Okay, so you have 2x plus 1, grouping symbols, plus 4x minus 9. So you have here 6x minus 8 for the sum of the two functions. And if you're going to subject this into the limit, you will have limit of f of x plus g of x as x approaches the same value of 1. That's limit of 6x minus 8 as x approaches to 1. Let me try to move a little bit here. All right, just like that. We have here, so by substitution, 6 times 1 minus 8, you will have a result of negative 2. See what happens here. Okay, the same value as of earlier. This is what the limit theorem stands for. That if you're already sure that your the limits already given, and if you're going to add them, no need to use this one here. But of course, you can try using this if you would like to verify your answer. But no need to use this, because you simply need to subject the limits L and M into the operation used. Okay? This limit theorem also works for difference. So let me increase here some spaces and proceed to the difference. What if I have, and I'm going to use h of x. I'm going to use here the limit of the difference of g of x and h of x as x approaches the same value of 1, because I already have the limit for g of x here. So if we have here like that, the limit of h of x as x approaches to 1, h of x is actually 6, if I'm correct, 6 minus x as x approaches to 1. By substitution, you have 6 minus 1, you have a result of 5. So this limit theorem automatically tells us that we simply are going to the notation used for g of x earlier was m and n for h of x. So m minus n, m minus n. M is this was g of x, so negative 5 and minus 5 here, which will give us a result of negative 10. This is by using of the limit theorem. Okay, but if we are going to illustrate that further by really getting the entire value of this, you will have g of x minus h of x is equal to, that's 4x minus 9 minus 6 minus x. Okay, those are the equivalent functions. 4x minus 9, don't forget that as you remove the grouping symbol, distribute that, minus 6, that's plus x. You will have here 5x minus 15. That's the difference of g and h. So if we're going to solve for the limit of the difference, g of x minus h of x, as x approaches to 1, take note, this should be the answer. Okay, that was the using the limit theorem earlier. So we'll have here the limit of 5x, this one here, minus 15 as x approaches to 1. By substitution, 5 times 1 minus 15. Okay, this would be 5 minus 15, we'll have negative 10. As you can see, we have the same result as here and here. This is using the expression out from their difference, but this already is using the equivalent limits as already solved. Okay, so just like that, we have the same result. So what if I have here last form, the limit, because this theorem could also be extended into more than 2. So we have here f of x minus g of x plus h of x. Okay, as x approaches to 1. We don't need to give the exact expression equivalent to this. Simply apply or use their limits. The limit for L is 3, then for M is negative 5, and then positive 5. So we have here 3 minus negative 5 plus 5. This is L, this is M, this was N. The result is 3 plus 5 plus 5, that's 13. If you would like to verify if this is correct or not, you can give the expression equivalent to this expression and solve the limit as it approaches the same constant 1, and I'm sure it will also result to 13. So this is what this limit theorem tells us. If you already have computed limits for separate functions, no need to come up with one singular expression for their sum or difference or a combination of both. Simply use their limits to solve for the limit of the entire general expression. So what are you waiting for? Subscribe now!